Okay, we're going to take a quick look at sections 2.1 and 2.2, which talks about relations and functions, and then also slope and rate of change. So things that we've encountered before in algebra and geometry. We're going to do a pretty quick review here. Focus on some of the things that you may have learned in algebra and geometry that are going to be more part of what we do in algebra 2. For example, domain and range is something that we're going to deal with quite a bit. So let's start with that. A relation is a mapping or pairing of input values to output values. Input and output values are also referred to as the domain and range, respectively. So the input values are the domain and the output values are the range. A function is a relation for which each input has exactly one output value. All right, so if you could take a quick look here at the representing relations diagram that we have here, there are four basic ways that we'll represent relations. Ordered pairs being one, a table, graph, and what's called a mapping diagram, which will actually show the input to output being mapped. So really we have the domain and range represented there with the input and output. So that's the first thing we start with are these two mapping diagrams. We're going to say whether a relation is a function or not. Remember, each input value has to have one and only one output value. So as we look at this here, kind of the concerning thing is the fact that the -4 has two input values mapped to it. That's okay. An output value can have two input values mapped to it. Okay, so this is a function. That's okay to have the two arrows going to the -4. Each input has only one output there. Now if we look at this second mapping diagram, this makes it not a function because the input value of 1 has two output values, the -1 and the 2. And it can only have one output value, so that is not a function. Another way to test if a relation is a function graphically is with a vertical line test. When you are performing the vertical line test, you're making sure that a vertical line will intersect the graph at no more than 1 point. So anywhere on the graph, if you can draw a vertical line, if it passes through more than 1 point, it is not a function. So this middle graph there is definitely not a function because pretty much anywhere we would draw a vertical line except for right there at the vertex, it would not be a function. So this is not a function here. The first graph that we have is a function. The vertical line would only pass at 1 point anywhere on that graph. And then we have two spots here where we fail the vertical line test, so this is also not a function. There we go. All right. Linear equations, or linear functions, actually change this to functions here. It's not a big deal. Linear functions can be written in the form y equals mx plus b. Graph of a linear function is a line. And we can rewrite y equals mx plus b using function notation, just simply replacing the y with f of x. A nonlinear equation has variables that are either degree less, excuse me, in a nonlinear equation, the variables are either of degree greater than 1 or less than 1. So anything that has a exponent of 1 on x is a linear equation. Nonlinear would be something like x squared, or square root of x, or 1 over x. Those are all nonlinear expressions. All right, the next examples ask us to evaluate some functions for different x values, a couple different ways you could do it. Y equals an expression, you can just be told to let x equal something. So here we're told let x equal 2. We're simply going to substitute that in and get 14. Here we have function notation. This means the same thing. Let x equals 2. Let x equal 2. We get the exact same thing here. It's the same question, two different ways of showing it. This next problem here, this is not linear because of the x cubed, so it's not linear. And then it's again asking us to let x equal 2. So we have negative 9 as our value. Let's wrap that up by actually saying f of 2 equals negative 9. That's pretty useful to write it like that because then we know that one point on the graph is 2, negative 9. Okay, so it tells us something about the function other than just y equals negative 9. All right, last one here. I'm going to put negative 2 in for x. Careful with the negatives. We end up getting 0. So g of negative 2 equals 0. That's actually pretty special. We're going to talk about this more in this class. When you evaluate a value for x and you get 0, that's actually a solution if we were to set this equal to 0, and it shows up as an x-intercept on the graph. And we're going to see that happen quite a bit in here.
I wouldn't even